Hi everyone, my name is Luiza Yerknapeshyan, and today I will be presenting my capstone research project on granular matter penetration testing supervised by Dr. Yerknapeshyan. Let's start by understanding what granular materials are. Granular materials are collections of microscopic particles that act collectively and interact through contact points. Familiar examples of granular materials from nature are sand, soil, gravel, snow, different kinds of food grains, and cereals. In terms of particle sizes, granular materials range from 1 micron to 100 meters, as this is the range where their interactions occur exclusively at contact points and are of predominantly repulsive nature. Larger objects, celestial bodies such as asteroids, planets, etc., have non-negligible gravitational forces pulling them together, and smaller particles such as powders have weak interactions such as van der Waals interactions between the particles, and even smaller particles known as colloids are subjected to thermal agitation, so they no longer exhibit the common properties of granular materials. So granular materials have, as a type of material, have a few very unique properties. That one of them is their material state. Unlike other types of materials, granular materials don't have a defined state of matter, but their state of matter behaves. It depends on the conditions. So, for example, when you're standing on a beach and compressing the sand with your feet, the sand will act like a solid and will not flow and will support your weight. However, when a bulk of granular material is tilted to a certain angle known as the angle of repose, it starts flowing like liquid. And when highly agitated, for example, during a sandstorm, granular materials will behave like gases. Granular materials are very interesting and important to study in nature to understand different natural phenomena such as landslides and avalanches, and understanding their unique behavior will allow us to be able to predict such natural cataclysms and maybe be able to be more prepared for them. Granular materials are also very common in the industrial sector. In fact, they make up around 70% of the industrial feedstock, and their applications range from construction and agriculture to food production and the pharmaceutical industry. In different industrial processes, granular materials often are subjected to different penetrative events, for example, during fracking or excavation or construction, and this penetration will cause a certain other very unique and defining property of granular materials, which is known as force chains. Force chains, because of the random packing, different particle shapes and sizes within a granular bulk and the various contact points between the particles, forces within a granular bulk will have preferred path of distribution, which are known as force chains. These figures depict force chains during impact loading and static loading. So, as you can see, granular materials have many different unique properties, and throughout the years, many methods have been developed to study those properties, which can broadly be categorized into experimental, analytical, and numerical methods. Experimental methods seek to quantify the behavior of granular materials through physical experimentations. Analytical methods seek to construct constitutive models to describe the behavior of granular materials, and numerical methods combine experimental data with constitutive models to simulate the behavior of a granular bulk. Some examples of the most common experiments on granular materials are brought in this table. Experimental methods could be further be branched out into data processing methods, such as the digital spectral photography, digital image correlation, X-ray computer tomography, which are can provide visual representations of granular behavior. But the most important test for our study is the penetration test, which involves driving a probe of different shapes, usually cones or wedges or plates, into a bulk of granular material, either in a lab setting or in situ, and with either a defined force or a constant velocity, and measuring respectively either the depth of penetration or velocity of penetration, or the reactive force acting on the load cell of the testing machine. And from the numerical methods, our study utilizes the discrete element method, which is one of the most widespread numerical methods to model granular behavior, and was first proposed in 1971 by Peter Condell, and has since developed to become one of the most utilized simulation methods. So the discrete element method involves modeling each particle, the contact points between particles, and the interactive forces between the particles, the angular momenta and the linear momenta on each individual particle, and using different simulation quantitative models, this can allow us to calculate the direction of motion, velocity, and acceleration of each individual particle, and the bulk behavior of the granular bed. Usually, DEM simulations are performed on spherical particles. Why? Because the contact interactions between two spherical particles are very well known. They are usually described by the Hertz contact law model, given in this equation. But as you can see from the delta term, this equation is highly nonlinear, making even the simplest case of two spheres interacting very complicated. So it is very difficult and computationally costly to perform DEM on non-spherical particles. However, spherical particles don't really represent the real granular materials that we will encounter in different applications very accurately. So a few different techniques have been developed to perform the DEM simulations on non-spherical particles, which usually involve either approximating the shape of a particle through a clump of spheres or through different analytical equations. And while these do work most of the time, they do not represent particles that have high angularity and have a faceted structure. And if you're working with such types of materials, these will not yield very accurate results. So the purpose of our study is to gather experimental data for granular material penetration tests on different particle shapes, and be able to extrapolate our data to a random polyhedral mesh of a particle, and be able to construct a model, a DEM model, to simulate the behavior of random polyhedral pack of granular materials. So the initial shapes that we considered were spheres, a clump of two spheres, a clump of four spheres arranged in a tetrahedral shape, a tetrahedron, and a more or less random polyhedral particle. However, due to time constraints and manufacturing difficulties, we settled on experimenting only on spherical, four spherical and tetrahedral particles, because these already constitute a wide range of polyhedral granular material shapes. The particles were modeled on SolidWorks and manufactured through fused deposition modeling, which is a type of 3D printing using PLA thermoplastic filament. This filament was chosen because it is very easy to work with, and the material properties, we wanted them to be constant across all particle shapes. Some of the properties are listed here, and also some of the particle properties that we measured, the average mass of particles and average density, are also listed in this table. So our experimental setup involved using a TIS resources universal test machine, and filling a rigid container with each shape of granular materials, and driving a plate-shaped probe into the bulk of the granular material, and the load cell of the machine recorded the forces on the reactive forces on the plate. We chose the method of constant velocity, and performed the penetration tests at 30 millimeters per minute, 60 millimeters per minute, and 100 millimeters per minute. And these are our test results. Some of the penetration tests were plotted here, and you can see there are many fluctuations in the graphs. These occur due to the local collapses in the material, and this is expected in a granular penetration. to be able to quantify these results, we calculated the mean force of penetration against the depth of penetration and the coefficient of variation against the depth of penetration. So the mean force will, in all three shapes, show a bimodal nature. So there is a first peak and then a trough and then a second peak. However, in spherical particles, it is way more defined, which is caused by which indicates strong formations of force chains, and at the bottom of the materials, as you can see, the force spike at the end is very steep. For tetrahedral particles, there's also a bimodal nature, but the peaks occur at different depths, mostly at mid-range and later. And this is due to the interlocking and randomness of the contacts. And the force sphere is more of a transitional shape for the spheres and the tetrahedra. And the coefficient of variation shows how repeatable the experiments are. The spheres have the least coefficient of variation because the initial packing of the spheres does not heavily influence its behavior. But for force spheres and tetrahedra, the very beginning is the variation is very large. This is caused by the interlocking, the very random packing of the materials within the bulk. And actually, the large spikes are due to the fact that very small absolute differences between the penetration forces will cause a large variation in the relative variation of the depth of the force penetration. So these indicate that for force spheres and tetrahedra, in the very beginning, the tests are very stochastic, very dependent on the initial randomness of the packing. However, starting from around 50 millimeters of depth, the variation settles, and it is more below 1 for all of the shapes. So the repeatability of the tests at these depths are way better. So in conclusion, our tests, we saw that the penetration tests the force of penetration is highly influenced by the particle shapes, as well as the force chain formation and stability and the repeatability of the experiments. And the spherical particles produce the highest deep depth penetration with reactive forces, which indicates a very strong formation of force chains at the at deep depths. For sphere clumps demonstrated an intermediate behavior between the particles, and the tetrahedra showed the most randomness in between the tests. And as these results can be used to calibrate the DEM simulations and to verify if our model of contact laws is accurate or not. So the future work will involve implementing our calibrated DEM simulations, which will be done by our partners at the Technical University of Delft, to be able to compare the results to the experimental tests and verify the accuracy of the contact model that was used in the DEM simulations, and make necessary adjustments if the results are if the discrepancy is too large. And actually, there is already a result from a simulation of a penetration test. This is a force chain formation on spherical particles, and this can further be extended using our experimental data. And then we would also like to see if the packing density or the initial arrangements of the particles will influence the penetration response, and if we have the capacity, we will also like to perform the penetration test on other particle shapes and other particle sizes. Thank you. If you have any questions, feel free to ask.
I have few comments in general to your work. You have done your experiments, mentioned the initial packing configuration. In fact, there are very simple steps to ensure uniformity of your packing, initial packing configuration, and ensuring that you are doing your experiment in a controlled and uniform manner. You can could do either vibration compacting of your granular matter or pressure compacting, because these are two variations that you come across in nature. All micro earthquakes are compacting on sands, etc., and the pressure of the overlaying ground or rocks can also compact the granular matter which lies under them, and that probably refers to your future work. And also you could do a little more work in terms of ensuring the size of your granules, that they are of similar size by filtering or sieving them, passing them through different sieves. Well, Press uniformly, and then force chains become much more predictable in that case. And then your experiments will become much cleaner.
Okay, thank you.
What are the alternatives for the alternative methods?
There are a few other numerical methods for studying granular materials. For example, the finite element method, smooth particle hydrodynamics, and material point method. But DEM is the most widely utilized method for studying force chains, and is more commonly performed in different literature.
Is there any statistical method? Because in this case, you are only working with a single particle, right? But the statistical information of the body is sort of lost.
Sorry, I don't understand.
So in this case, you are working for DM case, discrete element methods, you are working with a single particle, right?
Each individual particle is modeled with its individual contact points with other particles.
What about the statistical information? So between the interconnection of them, I wonder, I am not the expert here, just wonder if there is any method that can help us to understand also the statistical features of the materials without diving to discrete elements.
Statistic.
Anna, do you mean a variety of types of particles within one batch? Like there might not only be spheres or only be.
If you are considering a single element, you are also you are not taking consideration humidity. All the statistical effects you are not considering. But there's a statistical information, but there's impact on the material analysis.
No, DEM can be performed for many different arrangements of granular particles, and can be performed for not only dry granular materials, but also for saturated granular materials. We only need to know the physical effects acting on individual particles, and DEM allows us to model its motion and the bulk behavior of the granular materials using different physical laws. Usually we're considering the contact laws, but other physical constraints can also be put in the DEM simulations.
So as I understand from implementation point of view, the main interest should be in much smaller size particles, smaller scale particles, right? From implementation point of view. I mean, your test elements are very large. Can you, the test results transferable to the smaller size element?
Our goal is to understand if our contact model works for are polyhedral particles, and the testing on other particle shapes is part of our future goals for the study. So if we verify the law for larger particles, with some modifications, it can be extrapolated for particles of any size.
What are the industries? Like mining is the first thing that come into mind, but in Armenia currently that can be interested on.
Construction work, excavations, maybe different archaeological, what's the word? Research can benefit from understanding the behavior. Also, from the natural perspectives, natural phenomena perspectives, Armenia is very prone to landslides, so it can be also applied to that field, to studying. Yes?
I was wondering if so all of the tests that have been done with with identical particles, right? So no, for example, a combination of the spheres in a tetrahedral shape, they weren't combined with spheres.
No, the particles were separate, but it can be also orientation of future work to study the mixed behavior.
I was going to ask, like, is it worthwhile to study them because granular materials aren't always approximately the same size? There sometimes can be like a difference in shape to that effect.
Well, we segregated the materials so that we could have more control over the shapes and the responses. But maybe it can be determined by our future research that it is worthwhile to also mix different shapes of granular materials to ensure some randomness in the tests. Is there any other questions? Thank you.